Today we're going to be talking about the first derivative test. And let's look at this graph. I have a minimum down here and I'm increasing. My first derivative is positive. First derivative is 0, but I have no extrema because I keep increasing. First derivative then changes signs. So I have a maximum when f prime of x changes from positive to negative. And that's when our derivative changes signs. And then let's look and see where we have a local min. We have a local min right here where we change from when f prime of x, so our derivative changes from negative to positive. That's a key thing that you need to understand, a key application of our derivative. So our first derivative test. The following applies to a continuous function. You need to know this. You need to know and understand this. Make sure you have this written down. So a critical point. Remember, that's when our first derivative equals 0 or doesn't exist. And if I change from positive to negative, if I go from increasing to decreasing, we have a max. When I change from negative to positive, we have a minimum. And then if you don't change signs, then you have no local extrema. Now at an endpoint, if your first derivative is negative, first derivative being negative, then you have a local maximum. At a left endpoint, if your first derivative is positive, for x is greater than it, you're going to have a local minimum. And then at the right endpoint, if your derivative is decreasing for numbers less than our value of b, then you're going to have a minimum at that right endpoint. And then at our right endpoint, if your first derivative, if you're increasing for numbers less than that value of b, then you're going to have a local maximum. So getting into the actual problems here. Use the first derivative test to find the local extreme values. Identify any absolute extrema. So first I have to find my first derivative. I set my first derivative equal to 0 and solve. I'm going to factor that even more because that's going to be super helpful to us. So our critical points on our little number line are -3 and +3. And we're going to look at the sign of f of x. So use this equation. If I plug in a number less than -3, three is always going to be positive. This second factor, if I plug in a negative, I'm going to be negative. And then if I plug in a negative here, that factor is also negative. So I have a positive times by a negative times by a negative. That's going to be a positive, which means I'm going to be increasing to -3. Now plug in a number. Plug in 0. When I plug in 0, we have a positive always. So we really have to look at the signs of the last two. I have a negative times by now a positive, so I'm decreasing. Now if I plug in a number greater than 3 into our derivative, remember you're looking at the sign of the derivative. If I plug in, say, 4, we're going to be positive for all of them. which means I'm going to be increasing. So I need to find the local extreme values. That's the y's. So when I go from positive to negative, when our derivative goes from positive to negative, we're going to have a relative max. We're going to have a relative max of 57. I plugged in -3 into f of x to get that actual value at x equals -3. Because f prime of x changes from positive to negative. Now let's look and see what happens here at 3. I go from decreasing back to increasing. That means we're going to have a relative min of -51 at x equals 3. Again, I plugged in 3 into my function value to find out what that was. And this is because f prime of x changes from negative to positive. Now let's look at, just know what an x cubed graph looks like. You guys have an idea of what an x cubed graph looks like. It looks something like that. So we know that there is probably my relative max, there's my relative min, so we're going to have no absolute extrema. Our second example, using the first derivative test to find local extreme values here. So let's find our derivative, and we have a product rule. So derivative of the first function, leaving the second one alone, plus leaving the first alone, derivative of the second. I set that equal to 0, and I'm going to do some factoring. So we have when e to the x equals 0, which is never. We have when x equals 0, and when x equals -2. So again, do your little number line, and we're looking at what the sign of f of x is doing. So when I plug in a number less than -2, again, what I'm going to do is I'm going to plug it into this factored form so I can look and see. E to the x is always positive, so we really don't even have to worry about that. This x is going to be negative for numbers less than -2, and say if I plug in a number less than -2 here, we're also going to be negative, resulting in a positive, which means I'm increasing. Now from -2 to 0, plug in -1. The term that changes is this x plus 2 changes to being positive, so we would have a negative times by a positive. That means I'm decreasing because the first derivative is negative, and then greater than 0, all of those are going to be positive, so we are increasing. So we are going to have a relative max of 4 times e to the -2 at x equals -2. Again, I plugged in, I saw where our first derivative changed signs, changed from positive to negative, that told me max. I plugged in -2 into the original function for x, and then you need to tell me why. Okay, now we're going to have a relative min of 0 at x equals 0 because f prime of x changes from negative to positive. Now we need to determine if any of these are absolute extrema. It's hard for me to know what this function looks like. But what I'm going to do is I'm going to look at limits. The limit as x goes to -infinity of our function. Well, -infinity squared, that's going to be a pretty big number, but e to the -infinity, that's going to overpower our x squared. E to a negative number, a negative really big number, is going to get us really, really close to 0. So this limit is getting infinitely close to 0, but never equaling 0. So that means that we are going to have an absolute min of 0 at x equals 0. The curve, when you graph it on your calculator, looks something like this. Let me get some axes drawn for us. It comes from 0, has a little bit of a blip, goes back to 0, has that point, then goes up infinitely. And I used my calculator to graph that. I wouldn't expect you guys to know what that graph looks like. Okay, our next example is a particle moving along the x-axis. Find the velocity and acceleration and describe the motion of the particle given this function. So our velocity is our first derivative, and our acceleration is the second derivative of position. If I could find my derivative correctly. Okay, to describe the motion of the particle, we first have to figure out where it starts. So x of 0 at time t equals 0 is equal to 3. So the particle at a position of 3. I should say just starts at 3. Okay, now we need to figure out which direction it's moving. We look at our velocity curve for that. So I set my velocity equal to 0. So I set 4 minus 3t equal to 0. And that gets me 4/3 for a time when it's going to change direction. Also 0 is a key point, but 0 is where we started. So looking at our velocity curve, so for 0 and then 4/3, if I plug in 1 into our velocity equation, we're going to be positive here, and then we're going to change to negative. So our particle starts at 3, moving to the right, stops when t equals 4/3, and changes direction. And that was a fairly quick review. You should have remembered that from what we did earlier in the year. That's it for today. Please make sure your lesson summary is submitted on time.